Welcome back to the deep dive. We're here to really get into the details straight from the source material.
That's the plan.
And today we're talking about light, which, sounds simple, but it's fundamental. Specifically, the color of light and how it might be affecting, maybe even controlling, the shape of your eye.
It's a really big deal right now. I mean, the projections for myopia, for nearsightedness, they're, frankly, alarming.
Staggering, really, like
Mhm.
50% of the global population by 2050.
Exactly. Half the world. Well, it's a public health crisis brewing,
Yeah,
and it means we need to think differently about what's causing it.
right. We all sort of know the standard advice, get outside more. It helps protect against myopia.
Mm.
But why? Is it just that it's brighter outside?
Or is it something else? Like maybe the specific colors in natural sunlight are sending, I don't know, a stop growing signal to the eye.
A signal we might be missing indoors under artificial lights.
That's precisely the question this new research we're digging into is trying to answer. So our mission today, explore this study looking at the immediate short-term effects of specific colors, cyan, red, and blue light on the human eye.
Not long-term changes, but like what happens right away.
Exactly. Instant physiological reactions.
Okay, so to see those reactions, they had to measure the eye itself. What were they looking at?
Two main things. First, the eye's total length from front to back. That's called axial length, or AL.
Right, and if your AL gets too long, that's when you become nearsighted, right?
That's the primary issue in most myopia, yes. The eye elongates. Second, they measured the choroidal thickness, or CT.
The choroid. Remind me.
It's a really important layer of tissue, packed with blood vessels, sits right behind the retina. Changes there, especially rapid thinning, often go hand in hand with the eye getting longer, with myopia progressing.
Got it. AL and CT. So how did they expose people to these specific colors?
They developed this pretty clever tool, custom-made light-emitting glasses, basically goggles with LEDs inside.
LEDs.
Okay.
Yeah, positioned really close to the eye, just 4 centimeters away. This let them deliver quite specific wavelengths, precise colors.
Like what, specifically?
Cyan light at 507 nanometers, red light at 638 nanometers, and blue at 454 nanometers. And they compared the effects of these colors to just standard broadband white light, which was the control.
And who were they testing this on?
2 groups, which is important. 44 young adults, aged 18 to 28.
Okay.
And also 20 children, aged 8 to 15.
So they're looking at both kids, where myopia often starts or progresses rapidly, and young adults, to see if the eye still responds this way later on.
Exactly. Does this mechanism persist? That was a key question.
Okay, let's get to the results. The big goal is stopping that eye elongation, stopping AL growth. So what happened with the cyan light, that 507 nanometer one?
Well, this was the really striking finding. Compared to the regular white light, putting on those cyan light glasses for 2 hours caused a significant reduction in axial length.
Wait, reduction, the eye got shorter. Yes, acutely shorter. And at the same time, the choroid, specifically the bit under the fovea, the SFCT, got thicker.
Wow. So shorter eye, thicker choroid, both seem like good news if you're trying to fight myopia.
Precisely. Those are the exact opposite changes you see when myopia is progressing rapidly.
Okay, but these are eye measurements. We're talking tiny amounts, right? How much shorter did the eye get in the young adults?
In the young adults, over those 2 hours, the AL reduced by about 0.0100 millimeters, so 10 microns.
10 microns.
Yeah.
Sounds minuscule.
It is tiny, but you have to remember the context. Normally, eyes, especially myopic ones, are slowly getting longer. So even a temporary reversal, shortening of 10 microns in just 2 hours, is actually a pretty dramatic physiological response, statistically significant for sure.
And the choroid thickening.
That was about plus 0.008 millimeters in the adults. Again, small number, big biological implication.
Okay, and you mentioned this wasn't just like a brief twitch while the light was on. Did the effect last?
It did, and this is maybe the most fascinating part for the adults. That reduction in eye length, the AL shortening from the cyan light, it was still measurable, still significantly shorter than baseline, a full 30 minutes after they turned the cyan light off.
Whoa. So the effect persisted even after the stimulus was gone.
Yeah, it suggests that the cyan light triggered some kind of, ongoing biological process, sent a message that kept echoing for a bit.
Okay, that's adults. What about the kids? Were their eyes, maybe more pliable, more responsive?
They were, actually. In the 8 to 15-year-olds, the cyan light triggered an even stronger effect.
Really?
Yep. Their axial length reduced by about 0.016 millimeters.
16 microns.
16 microns. And the choroid thickened even more, too, about plus 0.014 4 millimeters. So yes, the younger eye seems even more sensitive to this particular stop signal from the cyan light.
Okay, so cyan light seems to be putting the brakes on eye growth, at least acutely.
Seems that way.
But what about the other end of the spectrum? They tested red light too, right? 638 nanometers.
They did. And the results were, well, the exact opposite.
Opposite, as in?
As in, exposure to the red light caused a significant increase in axial length. The eye got longer. Longer, and the choroid got thinner compared to the cyan light condition.
So red light, under these conditions, seemed to do exactly what you don't want if you're worried about myopia. It promoted elongation.
That's what the short-term data suggests, yes. Compared to the neutral white light, the red light caused the AL in young adults to increase by about 0.007 millimeters.
7 microns longer.
In just 2 hours. So you've got cyan shortening the eye, and this specific red light lengthening it. A clear opposition.
Okay, polar opposites. What about blue light? They tested that too, but only in adults.
That's right, just the adults for the blue light at 454 nanometers. And it also showed an inhibitory effect, like the cyan.
Ah, so blue also shortened the eye.
Yes. A small but significant reduction in AL, about minus 0.0007 millimeters compared to white light, especially noticeable after about an hour. But while blue light did shorten the eye a bit, the cyan light was much more effective at causing that choroidal thickening, which seems to be a really important part of the protective response.
So cyan was kind of the winner for the combined effect, shorter AL and thicker choroid.
It certainly showed the strongest overall inhibitory profile in this study, yes.
Okay, this is already fascinating. But then it gets even more layered, doesn't it? Because these effects, they weren't the same for everyone. It depended on whether the person was already nearsighted, a myope, or had normal vision, an emmetrope.
Exactly right. The baseline refractive state of the participant really mattered, particularly for how they responded to the cyan light. It wasn't a uniform effect across the board.
Okay, let's unpack that. Start with the young adults again. Where did the cyan light have the biggest, most lasting impact?
So for the young adults, that sustained shortening effect, the one that lasted 30 minutes after the light went off, was most pronounced in the participants who were already myopic.
Ah, so the nearsighted adults had the strongest, longest-lasting break signal from the cyan light.
That's what it looked like. It's as if their already elongated eyes were perhaps more receptive to that specific pullback signal, or maybe the signal just had more room to work, you could say.
Okay, that sort of makes intuitive sense.
Yeah.
But then you look at the children, and the pattern flips.
It does. And this is really interesting and raises some developmental questions. In the children, the significant shortening of the eye from the cyan light was seen mainly in the emmetropic kids.
The ones with normal vision.
Yes. The kids without myopia showed the strong response. But in the myopic children, the study actually found no significant change in their axial length from the cyan light in this short time frame.
Wait, really? So for kids with normal vision, cyan light is a strong break. But for kids already myopic, the break didn't seem to work acutely.
In this specific short-term experiment, yes, that's what they found. It suggests something might be different in the signaling pathways of a young, developing myopic eye compared to a young emmetropic eye.
Like maybe they're less sensitive to that specific color cue already.
Possibly. Or perhaps their retinal neurochemistry has adapted in some way. It's a really provocative finding that needs more investigation. Why would the normally sighted kids respond so strongly, but the myopic kids not show that immediate AL change?
Okay, so that leads us to the big why. Why these specific colors? Why these opposing effects? And you mentioned the setup earlier, the glasses being super close to the eye.
Yes, 4 centimeters, and that's absolutely critical to understanding the why.
Why? What does being that close do?
It creates a massive amount of optical blur. Think about holding something right up to your eye. You can't focus on it, right?
A total blur.
They calculated it was about 30 diopters of hypereropic defocus. Basically, the image formed by the LEDs was way behind the retina. It means the eye wasn't getting any useful focus information.
Ah, okay. So the eye's usual system for adjusting growth based on whether an image is focused in front or behind the retina. Yeah. That system was basically offline here because of the intense blur.
Exactly. It couldn't be using traditional optical defocus cues, which leaves only one explanation for these rapid changes in AL and CT.
The color itself.
Yeah.
The wavelength.
Precisely. The eye must be responding directly to the wavelength-specific chromatic cues. It's the energy, the frequency of the light itself triggering these changes, completely independent of focus.
And that connects to specific cells in the retina, doesn't it? That cyan light, 507 nanometers, that wavelength rings a bell.
It does. It falls right within the peak sensitivity range of melanopsin.
Melanopsin, that's not for regular vision, is it? That's more for like circadian rhythms.
Exactly. Melanopsin is found in a small subset of retinal ganglion cells, the MRGCs, and it primarily drives our non-visual responses to light, setting our body clock, controlling pupil size, sleep-wake cycles.
So the theory is that this non-visual light pathway, the one involving melanopsin, might actually be involved in regulating the physical growth of the eye.
That's the strong implication here. The cyan light hitting melanopsin, perhaps along with input from rods or cones too, seems to be triggering this cascade that results in choroidal thickening and axial shortening. It's a potential link between our body clock system and eye growth control.
That is, yeah, that's a huge potential link. A different way the eye might be controlled. And did this basic sensitivity, this ability to respond to the colors, change much between the kids and the adults?
Interestingly, no. When they looked at the maximum changes in AL and CT after the full 2 hours, the size of those changes was actually quite similar between the young adults and the children.
Really? So the fundamental mechanism seems intact.
It suggests that this acute response system to specific wavelengths doesn't just disappear after childhood. It's maintained into early adulthood, which is pretty important.
Yeah, because it implies that maybe interventions using light could still be relevant for young adults, not just kids.
Potentially, yes. The systems influencing eye growth might be more plastic, more responsive, for longer than we sometimes assume.
Okay, but we need to address something that might be confusing people.
Right.
The red light finding.
Right. The conflict.
Yeah. This study found that their specific red light, 638 millimeter LED, caused the eye to get longer and the choroid thinner. Bad news for myopia.
Correct.
But people may have heard about red light therapy, sometimes called RLRL, repeated low-level red light, being used in clinical trials, apparently quite successfully, to slow down myopia in kids. How can both be true?
Yes. This is crucial, but it comes down to the specifics. You absolutely cannot equate all red light treatments. They are very different technologies.
Okay, how so?
The successful RLRL therapies use low to moderate power laser diodes, semiconductor lasers.
Lasers, okay, not LEDs like in the study's glasses.
Correct. This study used low power LEDs. That difference is likely critical.
What's the difference between laser light and LED light in practical terms for the eye? Is it just power?
It's partly power, but also how the light is delivered. Laser light is coherent, it's much more focused, delivering a very precise dose of energy. LEDs are more diffuse. And importantly, the RLRL therapy involves short, repeated bursts of this laser light, maybe a few minutes a day. This study used a single, continuous 2-hour exposure to LED light.
So different light source, different power level, different delivery pattern, continuous versus pulsed.
Exactly. Those methodological differences, laser versus LED, power timing, almost certainly explain why you see opposite results. One, RLRL laser therapy, seems to inhibit myopia progression in trials, while the other, this specific LED exposure, acutely promoted elongation-like changes.
So the message is, the type of red light and how you use it matters a lot.
Absolutely. You can't just shine any old red light at an eye and expect a specific result. This study is a good reminder of that. Delivery method is key.
Okay, that clears up that apparent contradiction. Were there any other sort of secondary changes they measured in the eye besides the big ones, AL and CT?
Mostly, no. Things like the thickness of the cornea, the depth of the vitreous chamber behind the lens didn't really change significantly, but there were a couple of smaller, interesting findings. In the emmetropic young adults, the ones with normal vision, they saw a significant increase in the anterior chamber depth, the space between the cornea and the iris limbs.
Okay.
And in the myopic children, they noticed a significant thinning of the crystalline lens itself when exposed to both cyan and red light. The implications of those are less clear, but they were noted.
And limitations. Every study has them.
Yeah.
What did the researchers flag?
Yeah, they acknowledged a couple of main ones. First, as we mentioned, they didn't test the blue light in the children. That was due to sort of safety considerations and just the burden on the kids for longer testing.
Understandable.
Second, the participants they recruited only had mild to moderate myopia. So we don't know from this study if these same acute effects would happen in people with high myopia or very rapidly progressing myopia. Their eyes might respond differently again.
Right. Okay. So let's try and wrap this up. This deep dive shows a really dynamic, immediate response of the eye to specific colors.
Yeah.
What are the absolute key takeaways for listeners?
I think the biggest one is this clear wavelength-dependent effect on eye shape in the short term. Cyan light, around 507 nanometers, acts like a powerful rapid brake, shortening the eye, thickening the choroid.
Good signals.
Good signals. Whereas red light, at least this 638 millimeter LED version delivered continuously, did the opposite, acted like an accelerator, promoting elongation and thinning.
Opposing forces. And these effects aren't just for kids. The basic mechanism is still there in young adults.
Correct. That sensitivity persists. But, crucially, how the eye responds, especially to that beneficial cyan light, seems to depend on whether you're already myopic or not, particularly in childhood.
Right. The myopic kids didn't show that immediate shortening with cyan, while the emmetropic kids did. We can't just apply one rule to all eyes.
Exactly. Nuance is key.
So, final thought for people to chew on. Given that our eyes, even into adulthood, are this sensitive to specific colors, these chromatic cues, what does this mean for our indoor lives?
That's the big question, isn't it? If natural daylight has this potentially protective cyan-green component sending stop signals, what are our indoor lights doing? Our LEDs, our screens, they often have very specific, sometimes narrow, spiky spectral outputs.
Could the lack of certain wavelengths or the overabundance of others in our artificial light environment be subtly messing with these signals, maybe even encouraging eye growth over the long term?
It's a question we absolutely need to be asking. This research is about acute effects, but it opens the door to thinking about the chronic cumulative impact of our modern light diet. How should we be designing indoor lighting for long-term eye health, not just for energy efficiency or visual brightness? That's something to really think about.